Before our study of Newton's universal law of gravitation, we said that the potential energy between an object and the Earth was equal to mgh, where m is the mass of the object, g is the acceleration due to gravity of the Earth, and h is the height of the object's center of mass above some given reference point, which we often pick to be the ground. The catch is that this equation is only useful when the object is near the surface of the Earth, where g is constant. Following our study of Newton's universal law of gravitation, we learned that there's a more general equation for the potential energy between any two masses. So let's say that you have object with mass m1 and another object with mass m2, and they're separated by a distance little r. The gravitational potential energy of this system is equal to minus big G times m1, the mass of the first object, times m2, the mass of the second object, divided by r, where r is the distance between the centers of mass. Note that there's a negative sign, and unlike the force equation, the r is not squared. This equation is actually derived from the work done by gravity in moving these two objects from some infinite distance apart to this distance r apart. So let's figure out why this negative sign makes sense. Let's say that you're infinitely far away from Earth. So here's the Earth, and here's you some infinite distance away. Since you and the Earth are so far apart, you're basically not affecting one another. So we say that at an infinite distance away, the potential energy between the system of you and the Earth is 0. Let's say that I give you a little nudge towards Earth. Now, as you move closer to the Earth, the gravitational force between you and the Earth increases, and you start to speed up. So here you'll be going a little bit faster, and as you get even closer, you'll be going even faster. So as this is happening, what's happening to your kinetic energy? Well, you're speeding up, so your kinetic energy is increasing. So what must be happening to the potential energy of the system? Well, if the kinetic energy is increasing, and we know energy is conserved because gravity is a conservative force, then we know your potential energy has to be decreasing. But since the potential energy started at 0, the only way it can decrease is to become more and more negative. So that's why this negative sign makes sense. We're going to investigate 3 different situations concerning this negative potential energy. 1, where an object launched off the surface of a planet comes back down. 1, where an object launched off the surface of the planet escapes the planet's gravitational pull. And 1, where a satellite is bounded to the planet in a circular orbit. So our first situation is a rocket that we're launching off of this planet. So the planet has a mass of mp and radius rp. The rocket has a mass of m rocket or mr, and you're shooting it up with an initial velocity of vi. Now, of course, the rocket's going to be slowing down, and eventually it's going to stop and then turn around and come back and again hit the planet. If the initial velocity is large enough that it goes up pretty high, then the acceleration due to gravity is no longer 9.8 meters per second squared, so we can't use mgh for our potential energy. Instead, we need to use our more general gravitational potential energy equation, which again is minus g m1 m2 over r. So let's go ahead and figure out how high this rocket can go. So since the only force acting here is gravity, again we can say that energy is conserved. So we can say that our initial potential energy plus our initial kinetic energy will equal our final potential energy plus our final kinetic energy. Now, when you solve this problem, you need to be really careful because oftentimes students might guess that the initial potential energy of the system is 0 since this rocket is on the surface of the planet. But remember, when we use this equation, this term is only 0 when you're infinitely far away. So any other time, you do have a potential energy, and that potential energy will be negative. So for our initial potential energy, we have minus g, mass of the planet, times mass of the rocket, divided by r, which is the distance between the center of mass of the planet and the center of mass of the rocket. So since I'm starting on the surface, the little r is just the radius of the planet. Initially, the kinetic energy is the kinetic energy of the rocket. So we have plus 1/2 mass of the rocket times v initial squared. And then once it reaches this height, okay, we still have gravitational potential energy because we're not infinitely far away. So this becomes minus g, mass of the planet, mass of the rocket, divided by little r, which again is the distance from between the center of mass of the planet and the center of mass of the rocket, which in this case would be rp plus h. And our kinetic energy final, since we're trying to find this maximum height, that's where the velocity then would reach 0. So our kinetic energy would also be 0 up at the top. So since I'm solving for h, what I'm going to do is multiply this term by both sides to get it up on the numerator and divide both sides by this left term. So that'll give me rp plus h equals minus g mp mr over minus g mp mr over the radius of the planet plus 1/2 mr vi squared. And again, since I only want to know h, I can just subtract rp from both sides. So these things go away, and basically I get that h equals this term. So that tells me the height above the surface of the planet that this goes. Note that the initial velocity of the rocket wasn't large enough to actually escape the planet's pull. So we would say that this rocket was bounded to the planet, okay, because it went up, but it had to come back down. Now we're going to look at a case where the rocket can actually escape. But before we do that, let's look at an analogy. Let's say that you dig a hole into the ground and then you jump in. Now we're going to establish that this ground level has a potential energy equal to 0, and you down here are going to have a negative potential energy. So your potential energy is actually going to be minus 1,000 joules. We say that you're in a potential well. So how much energy would you need to get out of this well? Well, you'd need at least 1,000 joules of energy, right? So if I gave you positive 1,000 joules of kinetic energy, then you'd be able to escape and get back on the top. But if I only gave you 800 joules of kinetic energy, you would go up and then you'd fall back down. So if you can't escape, we say that you're bound to the well. But if you can escape and get back up to the top, we say you're unbounded. So to escape the gravitational pull of a planet, then we would want the rocket to be unbounded. So what would that mean? Well, if you look here, you already kind of saw that if you had a negative potential energy of 1,000 joules, in order to be unbounded, your kinetic energy had to balance that out. So to escape, basically what we have is that the potential energy plus the kinetic energy has to be greater than or equal to 0. This situation where your total energy is greater than or equal to 0 means that you are unbounded. Or in other words, you can escape the gravitational pull of the planet. So let's look at a new situation. Again, you're going to be launching a rocket off the surface of this planet. But this time, you want the rocket to escape. You want it to be unbounded. Our goal is to find the minimum velocity required to escape, and we call that the escape velocity. And again, we'll still give our planet m planet for mass, radius of the planet, and we'll give our rocket m sub r as a mass. So what we want to do is we want to find out what escape velocity we need in order for this rocket to no longer be pulled back to this planet. In other words, it can just go off into infinity and never come back. So we know in order to escape, or for the rocket to be unbounded, we have this energy consideration. So we can just plug in our equations for potential energy and kinetic energy and make sure that is greater than or equal to 0. So potential energy, again, is just our new gravitational potential energy equation, which is G, mass of the planet, mass of the rocket, divided by the distance between their center of masses, which in this case is the radius of the planet, plus the kinetic energy, which is the kinetic energy of the rocket, and that has to be greater than or equal to 0. So now if I just add this potential energy term to both sides, I get 1/2 mass of the rocket, velocity of the escape speed squared has to be greater than or equal to big G times the mass of the planet times the mass of the rocket divided by the radius of the planet. And you'll see here that the mass of the rocket is on both sides, so we can cancel that out, which means the escape velocity is independent of the mass of the thing that is escaping. So whether this thing is very massive or if it's really light, it doesn't matter because that mass cancels out. And now if we solve for the escape velocity, we get velocity escape has to be greater than or equal to the square root of 2g mass of the planet divided by the radius of the planet. So if that rocket has this speed, it will escape. For Earth, the escape speed is about 11.2 kilometers per second, which is about 25,000 miles per hour, which is pretty fast. So why do you think we care about the escape velocity? Well, if you wanted to work in space travel, of course, that might be a reason. But there's actually a much more important reason. A planet's escape velocity determines what kind of atmosphere it'll have. So if the molecules on a planet move faster than the escape velocity, they'd escape and they'd leave the planet. So that's why the moon doesn't have an atmosphere. Its escape velocity is so slow that the molecules actually are moving faster than that and they can escape. But for Earth, thankfully, this escape velocity is pretty fast, so we're able to keep a lot of our atmosphere here. I think that's a pretty awesome consequence of physics. So our final example is a situation where a satellite is orbiting a planet. So here you have a satellite in a circular orbit about this planet. Just with that information, we actually know a little bit about the energy. So since the satellite is in orbit, does that mean it's bounded or unbounded? Well, it has to be bounded because it's not escaping. So what does that say about the total mechanical energy of the system? Is it positive, negative, or 0? Well, you know if it's bounded, then the total energy, U plus K, has to be less than 0. But this is actually what we're going to try to find. We're actually going to find the total mechanical energy of the system. Okay, so the mechanical energy of the system is just U plus K. So our gravitational potential energy is minus G, mass of the planet, mass of the satellite, divided by the distance between their center of masses, which is little r, plus the kinetic energy, which is 1/2 times the mass of the satellite, times some velocity squared, but that actually wasn't given to us, right? We know this thing must be spinning around with some speed, but we don't know that value, so this is kind of what we need to figure out before we can go any further. So if we know that it is traveling in a circular orbit, can that tell us anything about the speed? Well, if we think back to Newton's laws, we know the sum of the forces equals ma. And so if we look at this satellite, what are the forces acting on the satellite? We have a force of gravity, Fg, and that's causing it to accelerate. And the force of gravity is just g, mass of the planet, mass of the satellite, divided by the distance between them squared. And since this force is causing this satellite to go in a circle, we know that the acceleration is just centripetal acceleration. So we have m of the satellite times v squared divided by the radius of the circle. In this case, the radius of the circle and the distance between the two planets is the same. Okay, it's r. So from here we see that the mass of the satellite cancels. Again, the orbital speed is independent of the satellite, and we see that one of our r's cancels, and we see that v squared equals g times mass of the planet divided by r. So again, what that means is if you are some distance away from the planet in a circular orbit, you're going to have this speed regardless of whether you're a satellite, you're a moon, or you're just a little speck of dust. All those things are going to have this orbital speed. So we can now plug this into our energy equation. I get the total energy is minus g, mass of the planet, mass of the satellite divided by r, plus 1/2 mass of the satellite times g, mass of the planet, over r. And if I rewrite this, you get g, mass of the planet, mass of the satellite, over r, plus 1/2 g, mass of the planet, mass of the satellite, over r. You can see that now these two terms are the same. So I have minus 1 plus 1/2 of the same term. So that gives me minus 1/2. So I'm left with minus 1/2 g, mass of the planet, mass of the satellite, over r is the total energy of the system. Now, does this jump out at you at all? What this means is that for circular orbits, the total energy is equal to 1/2 times the potential energy. Because you can see the potential energy was this term, and this is now the exact same term with a 1/2 factor. So this becomes pretty important in astrophysics, and actually it's called the virial theorem and becomes important in other areas of physics too.